starting this session right now. I'm just sharing my PPT. 1 minute. Just get some permission. Is my screen visible? If somebody could confirm, it would be good. Hello? Not yet. Okay, I think I'm facing a small technical issue here, so let's just see. Now it's visible. Now it's visible. Okay, right. Great. Hi, good evening, everybody, and welcome to today's tutorial session on urban utilities and planning. We'll be looking at water supply, sanitation, and drainage. So for those of you who have attended the previous session, which was there last week, you might be familiar of how we proceed with this usually. So every week we conduct this so that we can put into application whatever we learn for that week on this particular NPTEL course. We will try solving certain problems so that we're sure that we understood the concepts and we're able to apply them when it comes to real problems. So let me briefly introduce myself. I am Jess Lu. I am a Prime Minister's Research Fellow at the Department of Architecture and Regional Planning in IIT Kharagpur. So I will be handling this weekly tutorial sessions for every Tuesdays. So these are the topics which we discussed in the this week's lectures. I hope most of you have completed all the lectures, or if you've not, it's okay. Like you can still take some time. I think you have to submit the assignments so and so. Before that, it would be good to complete all the lectures and attempt the assignments. So we looked at what are the different water supply, water demand, and how do we predict it, and what are the different types of water demand that we looked at: industrial, residential, institutional, all that. Then we looked at what are the fluctuations in urban water demand, what causes water demand, what is the role of government, and how do the government set the tariff, or how do we plan tariff for water supply. So this was what was discussed, and today we will not be going into each topic, but we will be looking at certain problems, and we will try to relate those problems to these topics which we discussed, and we'll see how we can solve these problems. So before we begin, there are certain ground rules and certain small rules so that the whole discussions becomes really smooth. So those of you who were there last week would already know this. So I'll just take a minute to discuss this with those of you who were not there. So we'll just go about question by question. So I have about 10 questions for today. Let's see how much we can do. So after each question, I leave around 2 to 5 minute windows where you can ask questions related to that particular question. So please, it's a request that you ask questions related to only that question at that time, so that we can complete the discussion on that question, and then we will proceed further. If you miss asking in that window, don't worry. Towards the end, we will have one 5 to 10 minute discussion where you can ask certain questions for the whole questions which were discussed, or anything related to what was there in this week's video lectures, tutorials, everything we can discuss. And yeah, so I think today, unexceptionally, we're facing some technical issues, like even to load the presentation, it took some time. So if my video or audio is getting stuck at any time, please put it in the chat box. But sometimes when I'm presenting, I might not see the chat box. So feel free to unmute yourself and let me know that it's stuck, or it's I'm not audible, or whatever. So yeah, let's get started. Oops. Okay, I think I'm facing one issue. My presentation just went off, right? Okay, something is there in the chat box. Okay, just give me a minute. Just give me a minute. I'll just sort this, and we can proceed. It should work now. Right. Is it visible now? It is visible. Okay, thank you. Thank you for the confirmation. But somehow my pen is not working, so let's just proceed with this and we'll see how we can go about. So, okay, the first question is that which of the following factors contribute as an explanatory variable for predicting temporal variation in water demand? So, we first need to know what causes variations and what do we mean by temporal variation. So, as by the word itself suggests, temporal means something related to time, like tempor means something which is related to time. So, here we're interested to find out what is a temporal variable or what variable changes with respect to time and how it influences, whether it influences water demand or not. So the options are given. So let's look at what are the different factors which influence water demand. So different variations. So there can be temporal variations, as we discussed, something related to time, and there can also be special variations. So uh, here again, the point is that when it's a temporal variable with respect to time, it changes. So temperature, that is every day the temperature can change. With seasons the temperature can change. So with respect to time, there is some variation which is happening. Similar is the case of wind speed, prices, population growth, income. All these factors keep changing. Whereas there are other factors such as the area of a house or the outdoor area that a house has, or the features of the house, or the household size, or the typology, or the education level of the people living over them. So these can vary with respect to different geographical regions, or we say that these are special variations. That is, for a region, this more or less remains constant, and with time, or basically within the duration of time where we are designing this utility or the water supply, much variations or much changes do not happen. So this is the question which is asked over here. So let's go back and let's see what are the options which are given to us over here. And can we try attempting this question? Can somebody give an answer on what are the different factors? And what is the answer for this particular question? Can somebody give me the answer out? It's population growth. Very good. Yeah, population growth. We just discussed. So here, what we're talking about is growth. So with respect to time, population is growing. So that's a constraint with respect to time. Right. So let's proceed on next to one numerical. So okay, this one I kind of need my pen. So okay, so basically we have to estimate the total fire demand for a small city, which is that is what is given over here. Let me just try connecting my pen once more. I hope it works now. Yeah, it's loading. Just today, for some reason, the internet is a bit so slow that I'm not being able to connect to my iPad to present. Okay, let's proceed. It's okay. So these are the three methods which we usually use to estimate fire demand. So the first method is mainly a conceptual method where we look at what is the actual amount of water which is required in a place based on historical experiences or based on assumptions that this much number of fire would happen. So it's actually given as the amount of water required per person. That is what we calculate. But the catch here is that we cannot use this for a huge population. We can only use it for cases where population is less than 50,000. And okay, so I think my pen is just not going to work today. So I think I'll just go here and here itself I'll write. So that how we do is that for this particular one, we calculate Q, which is equal to the number of fires which will be there in a particular region, multiplied by how much is the discharge in minutes, like in 1 minute. So basically, we will, if there's a pipe, then we'll have a radius. So through that radius, some amount of water would be flowing. So how much amount of water is flowing through that pipe in 1 minute? So that is what is given by discharge in minute into the duration in which the fire is happening, so that we get the total amount of water which is happening. And we also want to, if you, so this is the total amount of water which would be required, but we are talking about per person how much would be required. So this whole thing we would divide it by the total population which is there in that particular region. So this is the formula which we use over here. And the second method is that so this is again a empirical method. We just where we make assumptions and we calculate. So here we look at how much of water is required in kiloliters per day. So this is a very simple empirical method where we say it's equal to 100 times root p. So I'm just writing it as root itself, where p is actually our population. P is equal to our population in thousands. Like it's not the overall population, but we divide it by 1,000 and then we put it. Right. So sorry for the inconvenience that my pen is not working. So I'll just do it this way. So yeah, and the last one is the Kuchling's formula. So this is the most widely used. Sorry, did I just go back? Yeah, this is the most widely used method that is for this particular one. Again, this is an empirical method where we use a factor, that is we use, this is the factor that we use, 3128 times root of the population, which the same root p which we used here, it's the same method. So this is the most commonly used, but these methods can also be used if you want to find a quick estimate or a very rough estimate of how much fire demand is required, and also based on population. If the population is very less, then we can use this method easily. So let's go back to the question here. It's asked for a population of 45,000, and we know the number of fires which are breaking out. So if you observe over here, the Kuchling's formula or the second one, we did not need to know how many fires are breaking out in a region. It's only based on the population. That is, if you have so many number of people, then you would require so much amount of water for the fire demand. So let's go back. So here we've been asked about for a less number of population, we know the number of fire that's happening. We also know the duration for which the fire stays. So can somebody tell me which method we would be using? Hello, am I audible or is it stuck? The first one. Yeah, right. Very good. So we were using the first one. So let's go ahead and calculate this. So since the population is less, so we're using the first method. So can we quickly calculate this and then give the answer? Yeah, that's better. So I'm just giving you like some 2 minutes if you can quickly calculate and then give the answer. So there is one thing which you do not know over here. From the question, we know that the number of fire that is there is 3, that we know. Then we need to know what is a discharge in minutes. So that from our lectures, we've discussed that a discharge in minute is 110 liters per minute. That will be the discharge which is happening in liters per minute. So this is there. This is there in our lecture. So mostly a hydrant will usually have about 3 streams or 3 jets which can be pulled out from this hydrant, or maybe 4 or 5, like it depends on the hydrant. So each jet usually has a discharge of about 1100 liters per minute. So we're assuming that we're using one jet over here, and with that one jet which has a jet discharge of 1100 liters per minute, we're using to extinguish this fire. And we also know the duration, that is the number of the time in which it's going to stay. Was it not 3 hours? It was 3 hours, right? So, and we also need the time. So discharge is so okay. So all the problems that we will be doing today, we would have to take adequate care on the units that we're using, because most of the formulas would be given in one particular unit, and if we don't convert the numbers, figures which we have into that unit, we will end up with wrong answers. So here the discharge is in minutes what we have. So the time which is given in our question is given in hours. That is, it's given as 3 hours. So it's important that we convert this. So 3 into 60. So we are converting this. And now the whole thing divided by the total population. So that'll be whole thing divided by, it was 45,000, right? The population. Yeah. So I think this is a very easy calculation. If somebody can calculate and then tell me, it would be nice. One sec. I think someone's joining. Yeah. Okay. Yeah. I'm sorry. The chat box, I might not see that because when I'm presenting, I'm not being able to see that. That's one problem. So if you can speak out, that would be better. Then I'll be able to know that you're saying. So here, there is one more catch while you're doing the calculation. If you can listen for a minute, the question asked, if you look at the options, so that's where in MCQ, when you're solving for competitive exams or even for the exam for our NPTEL course, if you have MCQ questions, we always need to look at the unit of the answer also. So in the answer it's given, it is kiloliters per day. So we want to find how much kiloliters per day. We do not want to find kiloliters per day per person. Like it's not for a person, but it is for the entire population. So now if we go back, what we get over here in the first formula is the amount of water required per person. That's why we're dividing by the population also. So we're going back to our calculation, we're dividing by the number of people. But if we want to find the kiloliters per day and not per population, we actually don't need to do this, like divided by 45,000. So eventually, like we get this and then we need to multiply it for the whole number of people. So we will end up multiplying by 45,000. So this can actually be eliminated and your final answer would be this. So you can simplify the calculation that way and make it much easier. So now this is very simple. I think you should be able to give me the answer very quickly. Yeah. So can somebody give me the answer? Is it there in the chat box? I'll just go check. First one, 594. Okay, yeah, Rahul has answered. Yeah, very good. It is option. It is option B, 594. Right. Let's go to the next question. So yeah, so the next question is very much similar to this. I'm again checking whether my iPad's getting connected. No, it's not. Yeah. So the next question is also very much similar to the previous one. So they've mentioned that you need to use Quichling's formula. So this formula we have already discussed how to use it. So let's just go straight ahead and answer this question. So this is very easy. So the population over here is given as, let's just go back. The population is 9 lakhs, so which means it's 9 into 10 raised to 5. So is that key? Yeah, I think you can do it. One second, I can't find that raised to. Yeah, okay, 9 into 10 raised to 5, and you divide it by 9 into, you divide it by 10 raised to 3 because you need it in 1,000. So eventually you get it, so I'll just write it here. So it'll be 9,000 divided by 1,000. So you'll get it as 900. So now we apply in the formula. I think it should be pretty easy to get this answer also. Yeah, so Rahul's answered that also. So yeah, so these are very straightforward questions. So I think it's very easy. So you just need to look, just to conclude, you just need to look at the catch of what is a unit. So here the unit is given as in liters per minute. So you need to ensure that whatever answer we're getting is also in liters per minute. So in this particular case, no conversion was required. We got it easily. So yeah, so the answer is option D, that is 9540 liters per minute. So yeah, so these 3 questions, whatever we discussed till now, if you have any doubts, you can ask right now. I'll just go back to the screen. Any doubts, you can even put it in the chat box. I've shared for a minute so that I've stopped sharing for a minute so that I can see the chat box. questions, fine. Let's proceed further. I'm just sharing it back. Right. So we're proceeding further to the next question. So this is again, so this question is on water consumption. So we looked at how do we calculate fire. So now water supply, how do we calculate? This numerical is on that. So what is the maximum hourly consumption when the average daily consumption is 300 LPCD? So LPCD stands for liters per person per day, like that is per capita, like per capita per day, that is LPCD. So here, the maximum hourly demand we want it in terms of LPC, that is it's hourly, so that per day is not there over there. So this is a question which is asked. So now first let's look into why do we think that there would be a maximum hourly consumption, or what causes this variation in consumption with respect to hours. So we've already discussed in the lectures that there are certain fluctuations which happen in the consumption. It's not a uniform consumption which would be happening, and the reasons for this. Hello, my screen's visible, right? I just got a notification, so everything all right, right? And somebody just confirm. Yeah, okay. Thank you very much. Yeah. I mean, sometimes these notifications can be a bit distracting. So, yeah. So, coming back, what causes this variations or fluctuations? So, there are certain reasons for this. Like it can be climatic reasons. That is, with respect to seasons, there can be variations. For instance, in summer we might consume more water, and in winter we might consume less. But in some places with extreme cold winter conditions, water consumption may even be more because you'll have to leave the taps open so that water doesn't get frozen. So such kind of seasonal variations can cause different consumption routine, and certain personal factors, or because of the personal lifestyle of people or behavioral choice, the daily and the hourly consumption can also vary in different places for different people. So but how do we capture, like when we are designing something, we need to, when we're designing pipes or when we're designing the supply system, we need to design for a particular amount. Obviously we need to consider the fluctuations and variations, but there should be a design value or a design point to which we design, so that usually is the peak value, so that it can cater to all these variations. So to calculate that peak value is why we calculate the daily maximum daily consumption and maximum hourly consumption. So this question, or the series of next 2-3 questions, will be based on this water supply maximum hourly or daily consumption. So how do we capture this? Like, what do we use? So for this, we have certain relations, or certain empirical formulas based relations, which has already been developed. So this has been developed after looking at certain behavioral patterns and how people usually consume. So these are now followed as certain norms. So it's a good practice to remember these. So for maximum daily consumption, that is once we know the average annual consumption, we take it as 180% of the average consumption. So we are actually like around 180 times, like 180 percentage more we are taking of the annual consumption. And for the maximum hourly consumption, we look at 150 percentage of the average daily consumption. So we are taking this daily consumption, or this is maximum, but I'm saying average daily consumption 150 times. So if that is the case, this is for maximum daily consumption, this is for maximum hourly consumption. So now if you want to find the maximum hourly consumption for the day with the maximum daily consumption, how much would that be? Like, can you tell me? The maximum hourly consumption is 150 times, so 150 percentage more. And we want to find of the maximum day, like the day with the maximum consumption. So it'll be again a 180 times, so 180 percentage times of the average daily consumption. So, sorry, average hourly consumption, because this is average hourly consumption that we want to find. So, of the average hourly consumption. So, this is roughly, it comes up to about 270 times the average hourly consumption. So, this formula will also be very useful for us. So, in this particular question, we've been asked to, sorry, I think I went to a very different question now. Yeah. So this particular question, we've been asked to find the maximum hourly consumption with respect to daily consumption. So that's, I think it's very easy over here. So we know that we know this relationship which is there. We have the average daily to calculate. So it'll basically be 150 divided by 100 into what is in the question. Can somebody tell me what's in the question? It's 300 LPCD. So yeah, so 300 liters per capita per day. Right. So that is the average daily consumption. So now we want to find what is the hourly consumption. Right. So we have to divide it by, like, this is for a day. So in 1 hour, how much it would be? That division also we need to do. So yeah. So what's the answer for this? It might be there in the chat box. Yeah. Right. So Rahul's getting all the answers very quickly, I think faster than me. So that's very good. Yeah, it's 18.75. Check. Just give me a minute. Right. Right. Okay. So yeah, so you're right, Rahul. This is the answer. It is, one sec, somebody else is also joined. Yeah. Yeah. So again, yeah, so Rahul, you're right. It's 18.75, which is option D. So is there any doubt on this particular question? Then we can discuss that. Any doubts? I'm just stopping for a minute so that you can ask doubts. No doubts? Okay, very good. So let's proceed further. My screen is visible, right? Just confirmation once more. It is visible, but we can't see the PPT. You can't see the PPT. Okay. One sec. I'll just share once more. Yeah. Asmita, thank you very much for being so prompt. It's good that you're answering like this so that I know where I am. So yeah, thank you very much. Yeah, so I think you can see right now, right? All good? There is some, I know there's some delay today. I'm sitting in the lab, but still there's some Wi-Fi issue today. But I think it's all right. Like you can see the PPT and it's all fine. Asmita? No, we can't see the PPT. You can't see it. Okay. This happens. Once more. Okay, Wi-Fi is a bit down here. So okay, let's not waste time. I'll just post the question in the chat box. You can try solving it within that because it's very close to what we were discussing right now. It's the exact same thing. So let's yeah. Okay, I put it in the chat box. Oh, my chat box is also very slow. Yeah, I put it in the chat box. Meanwhile, I will just try to fix this. Hello, am I audible right now? Yeah, so I've logged in from a different system right now. The only issue is that the system doesn't have a webcam. So let me just, yeah, Anurag, okay, yeah, that's good. You've got the answer. I know some issue is just totally unpredictable today. Let me just log in back to from this. Just in a minute, okay, in a minute. Uh, no, I don't think this is going to happen. Yeah. Okay, okay, that's an echo. One sec. Let's just. Right, I'm back to the system. I hope it's all right. Entire screen share. Right, is okay. Presentation is visible right now. Hope. Yes. Can someone confirm? Oopsie, I can't hear you. One sec. Mic just got disconnected. Yeah. Is my presentation visible right now? Yes. Okay. Thank you so much. Yeah. Yeah. So let's where we yeah. So we were at this particular question. So I think somebody posted the answer. Was it for question number 5 that the answer was posted? I don't remember. Anyway, okay, now I can't see that because I just logged in. So let's just try solving this together. So here we are interested in finding the maximum hourly consumption of the day with maximum daily consumption. So this formula, how do we do this? We already discussed. That is, we would be taking 1.5 times, sorry, we'll be taking 150 percentage into 180 percentage. So this is easy. I think within this time you could have solved it. So can somebody give me the answer for this? Rahul, okay, 22.5. So I think Rahul's been promptly answering all the questions. Very good. Anybody else? Okay, or basically, is there anybody who did not understand this and wants me to work this out? I will work this out, or else we can proceed further. So you can put in the chat box if you want me to work this out. Nobody's put it, so yeah. So I think anyway, I mean, I'll just tell you. So we just did 150 percentage into, or basically we already calculated that. So it's 270 percentage into 200 divided by 24. This would be because it's given in LPCD, that is per day is what we are taking. So that into 200. So this is the answer. So this comes up to 22.5. So it's a very easy calculation. There was nothing much in that because we already derived this and kept. So it was very easy for us. So let's go to another theory question right now. So what is a false statement concerning water supply over here? So here in such questions, the options can get a bit tricky because we might get very confused. So if we find any one option, like two strategies you can use. One is eliminating all the options which you feel are not correct. The other one is you look for the option which you feel is the correct one. So here we can try both strategies. So looking at the question, let's go with the first strategy where we see whether we know which option is wrong. So let's go into the first one, that is a 24-hour supply decreases wastage of water due to leakage. So is this right or is this wrong? Any comments? Does it increase or does it decrease water wastage due to leakage? It increases water wastage. It increases. Okay, so I think that itself gives us the answer that if you're saying it increases, then this is wrong. So let's just keep it at stand. And so we feel that this is the false statement. Let's just go to the other one, like constant pressure in the distribution system. There is a constant pressure in the distribution system for a 24-hour supply. So is this right? Any comments? Is there a constant pressure, or does the pressure keep varying? Any comments? No comments. Okay. So basically, when we have a pipe, the flow through a pipe is mainly determined by two things. One can be the aperture or the radius of the pipe, and the other can be the pressure difference within the pipe, like or the pressure drop. So basically, the pressure with which we sorry the pressure with which the water is being pushed from one end. So, what happens in a normal non 24-hour, non continuous supply? So, there's usually a morning supply and an evening supply or a fixed duration. So, that time with adequate pressure, the water is pumped from one end so that it reaches the other end. So, there's that pressure difference which is there, which needs to be maintained so that the water from one end can actually reach the other end. Like it's because of pressure the water moves. But when it comes to a 24-hour supply, water is constantly keeping on flowing, which means that at a particular point we take in the distribution system, there won't be any pressure difference because the pressure with which water is flowing over here is the same. Constantly we're keeping on pushing that same water. So there's a constant pressure which is happening in the distribution system. So this option or this answer which is given is actually right. That is, in a 24-hour supply system, we need to maintain that constant pressure, and this constant pressure is always the peak pressure also, because at all the time we are supplying water at the peak pressure. And this next option is whether maintenance would be required for joints and meters, like it would be required more for a 24-hour supply system or not. So what do you think? Like, maintenance required is comparatively more, or is it comparatively less? Can somebody give some comments on this? Anybody? Or I'll just go to the chat box. So Rahul says increases, so that was for the previous one. Required more. Okay. So Anurag says it's there more would be required. Anurag, would you mind unmuting yourself and saying why do you feel more would be required? It would be good. Or if not, you can even put it in the chat box. But if you can, yeah, that's good. Yeah. Due to constant supply with the constant pressure head, there will be some issues with the joints and the junctions of the supply, so which need regular or some frequent maintenance. So with the constant supply of the pressure supply, there is certainly an increase in maintenance. Very good, very good. Yeah, that's a very, very valid point. That is constantly you're putting pressure on the water, so the joints might get wear out very quickly. So you need comparatively more maintenance. That's a very valid point that you put in. There is also one more reason that is, as Anurag was saying, this might wear out, and if this wears out, and if you don't maintain within time, because it's a 24-hour supply, there will be more wastage of water which is happening. So that is what we discussed in our option A also, like a 24-hour supply. It can increase the wastage of water due to leakage if proper maintenance is not done. So that is also one factor why we need to constantly keep on monitoring whether there's some maintenance which is required, because otherwise the losses which can happen can be huge. Whereas in an intermittent supply, this can be it won't be much, because only for that particular time we will lose water, and after that we will not lose water. Right. So very good, Anurag. So yeah, so this is right. That is, more maintenance is required because of these two factors which we discussed. Does anybody want to pitch in any more factor which you feel would be valid for this one? No. Okay. Yeah. Let's and the last option is that metering reduces water pressure drop. Such a drop which is happening because there's a constant pressure which is going. But our answer over here is 24-hour supply decreases water wastage. Decreases wastage. It actually increases wastage. So we're going for the best answer. Right. So now let's go on to the next question. That is, so this is about coincident draft. So this is again a calculation question. So what is the coincident draft for a city with population of 1.5 lakh population with average water demand equal to 200 LPCD? And here we've been asked to use a particular formula. So let's discuss on what we mean by the coincident draft. So this a draft in general basically talks about demand itself, like it's demand only. And coincident draft is the water demand. So we looked into what is a peak water demand, and in that same area we are also discussing about what is the coincident demand which is there. And by definition, we talk about coincident draft. So I'll just discuss here. So our total draft that we are talking about in coincident draft is equal to the sum of, like, there are two options. Like the first one, so either it can be the sum of the maximum daily demand which is there in water supply, which we discussed how do we find that, plus the fire demand which is there, fire demand which is there. So this either it can be this, or it can be the maximum hourly demand. So we also discussed how do we calculate the maximum hourly demand for the maximum day, like hourly demand, which is there for the maximum day. So this is the formula. And how do we choose from this? It's the maximum of this, like if the maximum of daily demand plus fire demand is either this if this is more, or it's this if this is more. So we can, like, if we write a formula, then we can put it as it's either the maximum of this. So this is the total draft that we have. So now let's go back to our question. So we have given what is the population. So we know that the population is 1.5 lakhs, and we know the average water demand which is happening. So this is the average daily demand, because we have LPCT, like it's given liters per capita per day. So unit is important. And if we look at the unit which is asked for here, like it is MLD, which is million liters per day. So here we actually don't need the per capita. So again, we're looking at the units and we're trying to simplify the question further. Even though the population is given, we now need to rethink whether we need to use this information or not. And for fire demand, we've been asked to use Kirchling's formula, so that is okay. So let's get started with this question. So first, we will find what is the maximum daily demand, because we're trying to find this one, the sum of this. So let's do that together. So let's do what is the maximum daily demand. I think this you can do it. We just discussed how we find the maximum daily demand. We learned the empiricals for it. That is, we have 180% times what will be the average demand is what is there. So what is the average demand? So in this, again, the catch comes in the unit again. So we know that the average demand is 200 liters per capita per person, and we have 1.5 lakh population. So whatever we get here is, we also know that in the maximum, if we use a normal formula, what we get is liters per day. And yeah. So we need to get the answers in liters per day, because we have to get in million. MLD is the unit which is being asked. So it's 180 in 180 percentage into, so per person, if 200 is a limit, for 1.5 people, what would be the limit? So that is what we need. So sorry, 1.5 lakh people. So 1.5 into, yeah, correct. So this is the formula which we would be using over here. So can somebody calculate this and tell me what this is? Yeah, Rahul, the question might have been discussed in yesterday's session. So some questions might be a bit repetitive. The idea is 1 week, we have one tutorial. So um, some questions which were discussed yesterday can also happen today. You can get your doubts cleared it's all right. So yeah, so the numericals might repeat. If you've attended yesterday's session, then ideally it's not necessary that you attend today's session. It's an or, like either yesterday's or today's you can attend. So yeah, so if you can solve this, then it would be it'll be nice. So can somebody give me the answer for this? How much this is? So I hope this is clear on why we are multiplying it with this, and in the previous ones we did not multiply because it's here what we want to find is liters per day, and we do not want to find liters per day per person. So we are multiplying it by the population also. Right. So this calculation, anybody who has done the calculation, can you give me? Asmita or Anurag, Devasena, somebody? Am I not audible? ML, uh, can somebody give the answer? Okay, first, am I audible or is it this that you're calculating? Okay, let's just we will complete this question. I know today I had some technical issues, so I will extend the time a bit more. So yeah, so this we get it up to 54 mld. MLD means million liters per day. So basically, we get it as 5.4 into 10 raised to 7 is what we would be getting. So that we will convert it into 54 million liters per day, like MLD. Right. Okay. Am I audible? Like for the last time I'm asking, is it chat box? Yes, okay. Thank you, Anurag, for confirming because there was no response. I was getting a bit confused whether I'm audible. Yeah, okay. So I think then I will proceed further. Yeah, so that's the maximum daily demand we calculated. Now we will go ahead and calculate the hourly demand. So, the fire demand. So for fire, we already know the formula, like, and they have mentioned that we need to use Kuchlin's formula. So we will be using 3182 into root of, so in this particular one we need to have the population in thousands, so we'll divide that like 1.5 lakhs divided by 1000, and so I'm just putting it here, root of 1.5 into 10 raised to 5 divided by 1000. Right. So this is the formula. So this calculation is also very simple, and in fire, we know that the unit or what we're going to get over here would be in liters per minute, right? So we want to find it in MLD, like that is million liters per, yeah, million liters per day. So, okay, if you get this answer, it's a simple calculation. I think you can do it fast. So I'll just show the steps also. 82 into, so this calculation, it comes up to around 12.247, so which will now be equal to, so this is so if we calculate this, then we will get 3897.1.38, right? So this is what we're getting. So now this is again in liters per minute. So now we need to convert this into MLD. So that means it. So what is million liters? So that million we can convert, but it's liters per minute. So we need to convert it into day, like per day. How many liters per day? So we will have to convert minutes into days. So again, simple. So whatever answer we are getting, we will multiply it with 24 hours into, like, for every minutes. So now that works out to about 56.12. which can be approximated as 56 mld. Right. If there's any doubt in this fire calculation, you can show it right now. Yeah, Anurag, right. 56 point. Sorry, I was not checking the chat box. I think you put it before. Yeah, right. So it is 56 mld. So this we've got. So for the first portion, we can immediately do the sum and we can say that the first one, it would be 54 plus 56. So that is 110 mld is the one over here. So let's just put it here. So it should be the maximum of 110, or what is the other one like that we need to find. So what is the maximum hourly demand for the maximum day? So that is also, we've already discussed how to do that. So let's go back. Let's do that also over here. So again, we know that it is 20 to 70 percentage, right? So I'm just taking it an easy calculation. So 2.7 into average hourly consumption. So now here the average hourly consumption, how do we calculate? So average daily consumption is 200. So that for a particular person. So here again, because our unit is per day, we are multiplying it with the population that we have, that is 1.5 lakhs into, yeah, and now we need to convert this into hour, like this is per day, so by 24 hours. So you see some things like this conversion, like there is scope for us to simplify this. We need not calculate this because eventually what we need is mld, that is per day. So this into 24 would come, so we can remove that 24 off and our whole calculation simplifies to 2.7 into 2. I'm just leaving the thousands onto the other side so that calculation becomes easier. So this much into 10 raised to 7 is what we are getting. Yeah, into 10 raised to 7. So this calculation simplifies to about 8.1 into 10 raised to, so let's just make it as 81 mld. Right. So are you with me over here? I hope all of you got this answer as 81 mld. Right. So going back to our question that is over here where we want to find what is the maximum. So is it 110 or 81? Maximum of this we would be choosing, which is 110 mld. So going back to our question, we have that as option B as 110 mld. Right. So this is the calculation for this. I'll just wait for 5 minutes. If you have any doubts in this calculation, you can ask right now. Yeah, Rahul. Rahul, I'm sorry, this is a bit repetitive for you, but probably maybe only this question repeated. I'm not sure. But again, the idea is that the problems, more problems you do, it's good. So it's okay. You can do it once more. So yeah, so I think nobody has any doubts in this. So so we just have like I planned like around 2 to 3 more questions. So we'll just quickly go through them because in some technical issue I lost some time. So it's my you for some more time. So let's just go through those questions quickly and then we can wind up for today. So first one is which in water demand is mostly inelastic in terms of which of the following. So this is again, what do we mean by inelastic? So inelastic means that whenever there is some change which is happening in the factor, do the water demand change? So basically, if we have an X and a Y, then does a change in X cause a change in Y? And if there is a change in Y, then that means it's elastic. That means that there is change which is happening, or Y is elastic in terms of X. But if there's no change which is happening, then that means it's inelastic. So here they've asked about whether water demand, so this is our Y over here, is inelastic in which of the following. So let's go option by option. When income changes, do you think the water demand would change? Anybody? Anybody? Anurag, what do you think about this? Okay. Or Rahul, do you want to take this and say what do you think? Water price. Okay, so you're directly giving the answer. Very good, yeah. So water price is inelastic. Yeah, that's right. We have discussed it in our lectures also that water price is inelastic. Now the reason is that when I just go option by option, when income changes or lifestyle changes, so we would or people would require more water or there is a change which is happening. Even household composition and there are more people, then we need more water for all these people. But water price, like it's a very common thing. Like how many of us actually look at how much we're paying for the water and then decide not to use water? So we won't do that unless and until we're in an extreme situation. So in general, based on water price, our water demand does not change. It's water demand is mainly a lifestyle choice or a seasonal choice, or there are other factors, but water price is not usually a very, very important factor. Like only in extreme cases it becomes important. So yes, so the answer is water price. Very good, Rahul, for answering this. So let's go to the I think we can end with this question, that is, which of the following is not an example of macro scale interaction considering water demand? So we discussed about what is a macro scale interaction, what is a micro scale interaction. Let's revisit what we discussed. So micro scale is something which is concerning an individual or a household or a group of houses, that is a parcel. So that talks about at a personal level, that is individually people know each other and individually how contributing. But macro is related to a region or for an entire region, a process or a pattern which happens. So going back over here, let's try to relate which of the following would relate to a region and which of the following would relate to an individual. So over here, water resource planning. So it's for a long term. It's an individual cannot plan how water resources should be done. It has to be taken up by the government, municipality, or local governing bodies. So this is again a macro scale interaction. So here the option is that which of the following is not an example. So this is a macro scale interaction. Now change in risk assessment, that is also planned by the government. So that goes into the macro scale category. Now human impact on hydrological systems. So this is also again how to like we're more than human impact, like it's the impact on hydrological systems. So this analysis will also be done by an agency or by a larger group. It won't be at an individual level or a household level who would be looking into how they're impacting the hydrological system. So this also relates to the macro scale. So now what's the last one is the household ownership of water consuming appliances. So this one an individual can relate to it, or an individual can control this, how much they own and how much they consume, like so that they can control. So this is a micro scale interaction. So option D is the right answer over here, that is which of the following is a not a macro scale interaction. So yeah, so this is a very straightforward question right from the standard, so I think you can do that yourself. So that's all for the discussion. So now yeah, okay. I just saw the answers right now. Yeah, option D was the answer. Any discussions or any doubts regarding whatever we discussed? Yeah, Anurag, that is also 40 LPHD. Yeah, very good. That was also right. Great. So, any comments on how you would want to improve these sessions next week? We can have that discussion. Today, some technical issues with that. If you have any comments or any thing, we can, like 2 minutes, we can discuss and then we can wind up. Yeah, thanks, Rahul. Anybody else? Would you want to? Is there any particular question that you would like to discuss with the SN? In fact, last week I'd given one geometrical progression question, so but I don't see anybody who were there last week over here today. So if there's any doubt on that, that also you can put. So before we wind up, any doubts in this particular session or any doubts in any of the video lectures, you can put it in the discussion forum. If it's regarding this particular tutorial, you can even address me by my name and put it saying that it was from this Tuesday's tutorial or mine, Jeslo's tutorial. What is the purpose of coincident draft? So yeah, so that we're looking at the different peak demands, and in peak, so we saw basically in one word I would answer, it's mainly to design our water supply systems. That is how much of capacity should our pipes and the distribution system hold? For that we use. So there are three methods. The first method is we take the peak, just the peak amount. That is why we're looking at the maximum hourly demand, maximum daily demand, all that. The second method is where we're using this coincident draft, where we're considering both the fire demand also when we're calculating the peak, or we're just taking the maximum peak demand. So that is what we're doing. The maximum of that, like that is, in fact, the fire demand will also be included in the maximum of the maximum daily demand. So that's why we're taking the coincident draft. Draft again means demand. It's the same thing. And the third method is we use certain peak factors. That is, for a pump, we use this particular peak factor. For a supply system or a tank, a storage tank, we use this particular peak factor. So I can just, since you asked that question, I'll just show you that in presentation also where that is located. Um, so this is downloadable, right? You might have already downloaded this. So in the presentation, one sec, let me just go to that. This is fluctuations. Yeah, in fluctuations is where we actually, yeah. So this is where we are talking about fluctuations of demand. So this is what we were discussing. So this is the first method where we take the hour, and then comes our coincident draft. That is where we consider both fire demand also we consider, and eventually if the maximum hourly demand for the maximum day is more, then we consider that. So basically this also includes this mostly if we are taking. And then we also have this peak factors also, like based on population, we have certain peak factors which we consider that these are the peak factors. So this is governed as standards in the policies of the government. So in our next lecture, we looked into different policies. So these are already marked in these. And also for certain equipment also, we take certain peak factors. So that's all there. So these three methods are eventually leading on to how do we design the system, or how do we design the utility. So that's why we use coincident draft. So I think that answers the question. How do we decide the method to be used? Yeah, so as discussed, like mostly we take the maximum, that is we design for the peak, right? So maximum what is there. And if you actually calculate and then see, there won't be much of variation between all these methods. Like we saw, it was 110 LPCD and 80. Like if you're taking the maximum and if you're taking the coincident draft, this one, it was, so it's just that method. And the best way would be to check all the methods and then see which is the maximum and then decide for the maximum. But again, there are other factors also which considers. So in other factors like cost and all that would play a role. So going for the maximum might not be suitable when we have resource constraints or other. So as a general rule on what method do we use, like be it for designing our systems, be it for designing on what tariff must be used. So for all this, whatever we have learned in this entire week's lecture are certain factors which contribute. So in our last lecture, we're discussing about this, where we say that we take all these factors, we note them down, and we prioritize which is the factor that we need to give the most important, or which is the objective that we need to consider most important. That is, do we have to ensure that it meets the peak demand, or do we have to ensure that sometimes during the day when the peak demand happens, it's okay even if that is not met. It can be sacrificed. So it depends upon the location and how the situation is. So it's very much context dependent. So based on that, we prioritize certain factors. So the factors which we discussed. So after we prioritize that, we take the most important factor and we put that first, and then we take the next important factor and we adjust this factor so that the next important factor is also considered. So probably it would involve increasing or decreasing this most important factor. So like that, we iteratively keep on adjusting all the other factors. So this is the usual method that planners follow in order to design the systems, as well as design the tariff that needs to be collected for a particular system. So yeah. Any other doubts? Okay, great. So yeah, I hope you all enjoyed this session, and we'll see you next week with the tutorials for the next week's lecture. And I'm once again sorry for the technical issue that my pen was not working and this whole issue. You all are very cooperative. Thank you very much for that. Next week I'll get it sorted, and I hope things will run smooth next week. Yeah. So thank you all, and have a good evening. Yeah. Bye. Bye, Asmita. Bye.